friends of the world, welcome to the fourth video of the Q channel. In this video I am going to show you how to increase the efficiency of the airflow motor seen in the previous video significantly to convert it into a 24/7 domestic wind farm.
First of all, what do we mean by a 24/7 domestic wind farm? This is simply the combination of the basic airflow motor previously seen with an innovation of mine that I call a power efficiency booster or a PEB circuit. A PEB circuit is just a very basic electric circuit, and a special one which is placed externally alongside the airflow motor formed by the two turbines, as you can see in the picture here. It is a black box which contains a special circuit. I apologize for not disclosing the details of this circuit at the moment, because in order to do that I have to wait until the publication of a patent application I have filed already. As soon as this patent application is published, I will reveal to you all the information related to this PEB circuit so that you can implement it yourself and perhaps build your own domestic wind farm. But what I can assure you at this moment is that there is no trick or cheat involving this black box. It does not contain any magnetic device, nor any battery, nor any active device. It is just a very simple connection. By virtue of this PEB circuit, you can see that the efficiency of the previously tested airflow motor increases dramatically. In this video, we are going to determine the efficiency of this new machine, which I call a 200-watt domestic wind farm, which, the same as the basic airflow motor, uses a 200-watt 8-ohm low resistor as well.
This is the setup for measuring the efficiency of the 200 watts wind farm, domestic wind farm. Here we have the power supply. We're going to start with at the same voltages we used in the previous video. We start with 20 volts, then 24 volts, then 40 volts to compare the efficiency of both machines in both cases. Okay, here on the meters we have here, this is the input voltage meter. This is the input current meter, and this third one, this is the output voltage meter, and the last one is the blue one is the output current meter. Okay, now we are going to start switching on the power supply and starting with a voltage 20 volts. Okay, here we can see the values of the input voltage 1952, the input current 2.398 amps, the output voltage 1951 and not zero as it happened with the airflow motor, and the input current 2.381 amp. Now we are going to increase it to 24 volt to see what are the values for that particular voltage. Now we are going to increase the input voltage to 34. 34 volts. Now we have 34 volts applied to the input of the wind farm, the domestic wind farm, and you can see the values now of the input voltage as measured by the testers, input voltage, input current, output voltage, and output current. Now we'll increase the input voltage to 40 volts. And we have the new values of the input and output voltage and currents. I will increase a little bit more to see whether we can reach a power, an input power of 200 watts. Right now we have 189 watts. Let's increase it a little bit, maybe to 41, 41 or 42. Let's see if better 42. 42 volts. And now we can see that the power, input power from the power supply is 208 watts. That's what I call this wind farm, this domestic wind farm. I call it a 200 watts wind farm. Okay, let's take note of this particular values, and by using these values we are going to later to calculate the power efficiency of this machine, and we can compare it with the power efficiency of the basic airflow motor. We'll calculate the efficiency by using the equation given previously in the previous video for the input power, the output power, and the efficiency.
On the 200 watt domestic wind farm, we are going to calculate both the input and the output power and the efficiency of this machine, and we are going to compare these results with the values we obtained previously for the basic airflow motor. We do this comparison for a number of input voltages just to contrast the performance of both machines.
Is the previous measurements of the input and output voltages and current to the 200 watts wind farm. We are going to calculate both the output power and the efficiency of the wind farm. And we are going to compare it with the values we obtained for the basic airflow motor. And we'll do this comparison for a number of input voltages just to contrast the performance of both machines. First of all, at 20 volts input voltage to the basic airflow motor, the input power was 0.46 watts, and the output power was zero watts. Therefore, the efficiency of the basic airflow motor at that particular input voltage was just 0%. Remember that we were using the same load resistor for both machines. That is an 8 ohms 200 watts resistor for both machines. Okay, on the other hand, at 20 volts input voltage for the 200 watt domestic wind farm, the input power was 46 times 785 watts. Okay, of course, you obtain this multiplying the input voltage times the input current, okay, according to equation 1. And the output power obtained by multiplying the output voltage times the output current was 46.453. And then the efficiency of the domestic wind farm calculated using equation 3 was 92.29%. At an input voltage of 34 volts to the basic airflow motor, the input power calculated was 1.33 and the output power was just about 16 milliwatts or 0.0016 watts. And the efficiency turned out to be 0.088, not even 1%. On the other hand, at the same voltage, the same input voltage 34 volts for the domestic wind farm, the input power was 135.104, the output power was 134.165, and the efficiency was 99.31%. And then we have at input voltage of 40 volts to the basic airflow motor, the input power was 298 watts and the output power was 32 milliwatts. That is, it was 0.0032 watts and the efficiency was 0.107%, not even 1%. Let's compare this with the results for the domestic wind farm. At 40 volts, the input power was 186.294 watts, and the output power was 184.838 watts. And that gave us an efficiency of 92.22%. 99.22%. And you can see that with the domestic wind farm, which is just the same as the basic airflow motor, except that we attach a power efficient booster externally to the airflow motor, right? And this, by using this this PEP circuit, we dramatically increase both the output power and the efficiency of the machine, which is equivalent to say that
the PEP circuit performs as a convergent nozzle in the sense that it increases the velocity of the airflow that impacts the turbine blades.
And finally, let's see, for a voltage of 42, input voltage 42 volts, the input power was 202.782 watts, and the output power was 201.507 watts, and the efficiency turned out to be 99.37%. Observe that for the domestic wind farm, for all the voltages, input voltages we use, the efficiency is always greater than 99%. It's almost 100%, not quite. For example, for 42, an input voltage of 42 volts, the difference between the input power, which is 202.782 watts, and the output power, which is 201.507, is less than 2 watts. So maybe you could wonder whether it is possible somehow to achieve over unity, because unity is very close with this domestic wind farm. In the next video, we are going to be talking about a bigger domestic wind farm. In fact, it would be a 5 kilowatt domestic wind farm. And we are going to be discussing the possibility of getting over unity. And for this bigger domestic wind farm, we'll use as a basic building block the 200 watt domestic wind farm we have been so far talking about. And so I would like your opinion about, do you think it is possible to get over unity? Do you think it's reachable? I will wait for your comments. Until then, thanks for viewing.